This video is going to talk about the concepts of motion. So we're just barely starting our physics class, and we always start talking about motion in general. We are specifically going to talk about what we call linear motion, meaning whatever we're analyzing, a car, a ball, a person, we're going to analyze and look at the object moving in a straight line. That straight line could be back and forth. Say we're watching a car drive down the street or back up out of their parking spot in the parking lot. The motion could be straight up and down, like tossing a ball in the air and letting it rise and then fall back to our hand. That motion could be along an incline, say skateboarding down a hill, or a child sliding down a slide, but a straight slide. The reason we're going to start with straight line motion, we call it linear motion, is just to start on the easier end of things. Now, one other thing really quick is that we use what is called a particle model. What that means is anything, the car, a person, a ball, is going to be represented by a particle, something very small and compact. This allows us to ignore air resistance. So it is a big assumption. In some situations we talk about ignoring air resistance is not necessarily a bad thing. But of course, other situations, it's a terrible assumption. I mean, if we have a parachuter jumping out of an airplane, of course they need air resistance. That's why their parachute will work. So at this point, we would still consider something dropped out of an airplane a particle, so that we can ignore air resistance, so that we don't have to understand how to work with differential equations yet. So everything we talk about is going to be a particle. Now, in terms of concepts of motion, in physics, there are two categories of concepts that we talk about. We have what are called scalars and vectors. A scalar is just a number. We call this number the magnitude. Something like the height of a building or the height of a bridge. That is just a scalar. It's a number. Something like the weight of something. The weight of that pumpkin. The weight of that cantaloupe. Weight is just a number. Vectors require a number, which we do call a magnitude. But they also require a direction. For example, let's say I lived 15 miles from school. If I lived 15 miles away from school, and again, school being in downtown Salt Lake, or I guess Redwood is where my campus is. If I live 15 miles from school, I tell you that doesn't give you enough information to narrow down the town I live in. So I could live south, I could live east, I could live west, I could live northwest, southeast. What we refer to when we're talking about southeast, north, southeast, west is the direction. If I wanted you to be able to guess the town I live in based off of this 15 miles away from school, that would be a lot of options to guess from. But if I really wanted to help you and narrow down where I lived, I could say that I lived 15 miles north of school. And that would narrow down where I live. That's what we're referring to when we talk about a vector. A vector has a magnitude, a numerical value, and a direction. So in what way? North, south, east, west, up towards the sky, down towards the ground. So there are many concepts that we are going to cover that will be vectors. So in terms of where we're starting now with basic motion, our vectors are going to be our position. So position is exactly what I was just representing. 15 miles away, that's how far, and direction, north. So position in physics is how far away and what direction. Now, when we talk about directions, we always have to have some sort of origin to work with. The way I mentioned where I live, away from school, made school my origin. So we're always measuring position from some sort of origin, from some sort of location. When it comes down to working with vectors fully, we end up describing directions in terms of a coordinate system. So you've all worked with coordinate systems. We have the x-axis, the y-axis, the origin, of course, being right there in the middle. We will be using a coordinate system with a specific origin in order to solve problems where we're talking about position. Now, our author, in terms of variables, uses an S to represent position, to represent that it has a direction associated with it as well. We often put a half arrow above the letter to represent that it has a direction associated with it. If you use other learning resources, textbooks, Chegg, that sort of thing, some other common variables are R. If you think about in a coordinate system, say the polar coordinate system, and you were talking about a point out here, R would represent that straight line distance from the origin over to that point. So R is common to use, X is common to use, Y is common to use. When you get to 3 dimensions, which is not in this class, 3-dimensional motion is for your dynamics class if you end up taking that. So position you will see as S or R or X or Y. That always means how far away from a specific origin. Another vector that is common is actually something we use in our everyday, or at least a common usage in our language, and that is for velocity. Now, when we talk velocity, if we're going, hey, I was traveling this fast, we're typically talking about what we call the speed. Speed is a scalar. It's just a number. It represents simply how fast the object is traveling at whatever moment we look at it. If I'm driving down the freeway and I'm driving at 80 miles per hour and I happen to see the cop sitting on the side of the road, I am very worried about my speed at that moment. And I look at my speedometer to figure that out. Speed and velocity are not the same thing in physics. They are most definitely related. Velocity, because it is a vector, just like position is a vector, it has to have a numerical value, a magnitude. By magnitude, we mean an absolute value, so just how fast. So the magnitude or the numerical value of velocity is the speed, so how fast. But to make it velocity, meaning a direction as well, then our velocity, we have to say, well, I'm driving south, I'm driving west, whatever direction my car at that moment is traveling in, or what direction a ball, if I tossed a ball upwards and it's moving upwards and getting slower and slower, I would say the velocity points up. That's a direction. The speed would be changing as the ball goes higher and higher, because eventually it slows down, turns around, and comes back down. We know the force of gravity is acting on the ball, slowing it down, and then it would speed it up on the way back down. The velocity is a vector in that we need to know how fast the object is moving and what direction it is moving in. We use a symbol V to represent velocity. And again, we will oftentimes put a little half arrow above it to represent that it is a vector. Now, the other vector that is important in terms of motion is acceleration. Now, acceleration is another term that if physics is new to you, it has a different meaning that we tend to think of in our everyday world if we happen to talk about acceleration. The physics definition of acceleration is that somehow the velocity is changing. So change in velocity in some period of time. We write this, so A, lowercase a, we're going to use to represent acceleration. As an equation, we write this as a change. You probably have seen delta before to represent change. So a change in velocity per change in time, so some amount of time. Acceleration is a vector, meaning it has a direction associated with it, which we're going to talk about that more because that's really important to understand, and it's extremely important when we want to actually make calculations. Now, just quickly as a reminder, delta anything means the final value of that thing, so final velocity minus the initial value. So delta V would be V final minus V initial. Delta T would be T final minus T initial. This technically would give us our average velocity, which is fine. Now, we don't have a separate word for acceleration if we're just talking a magnitude of acceleration. For example, you may all, or some of you may know, the acceleration of gravity. We call this a lowercase g. It is 9.8 meters per second squared. That is a magnitude. Meaning just the number. We are not clarifying a direction here, and that's why it is just the magnitude. Now, we do know it points down towards the ground. Down is the direction. So acceleration, we can talk about just the numerical value of it, or we can talk about the numerical value and the direction. When it comes to solving problems and getting numerical answers for motion, we have to have the direction and understand the direction that things point in. So we're going to be talking about that as we go along. All right. I would ask you if you had questions so far, but no one is there to ask. All right, so a couple things really quick. Our everyday world, sometimes we talk about average velocity, but of course we actually mean average speed. For example, when I lived 15 miles away from work, it took me 15 minutes to get to work. Well, average speed, we could totally calculate that. We know speed is distance over time. So if I lived 15 miles away, but it only took me 15 minutes, 15 minutes would be a quarter of an hour. We would say that my average speed was 60 miles per hour. Well, I like to ask, does this mean I'm a slowpoke on the freeway? Well, it doesn't actually. If you remember what we mean by average value of a group of numbers, you always have to have a group of higher values and a group of lower values to average out as 60 in this case. So during the 15 minutes to get to work, some of the time I'm driving faster than 60. In fact, quite a bit faster than 60, because I have to average out with the times that I am stopped at the stop sign or the times I'm stopped at a stoplight. So I don't run through stop signs. I don't run through stoplights. I go slow through my neighborhood. So to average out those really slow periods of time or even stopped periods of time, there has to be much higher speed on the freeway to make up for that and to average out at 60. Now, if I'm driving down the freeway and I happen to see that highway patrolman sitting over there, he doesn't care, he or she does not care what my average speed is. They want to know what we call an instantaneous speed. Instantaneous speed, which of course is our speedometer, assuming it's working correctly. It's just how fast we're moving at the moment they clock us. Instantaneous values we're going to get to in chapter 2. What the velocity is at an instant in time, a specific moment, or the position at a specific moment, the acceleration at a specific moment. So we're going to build on that as we get into the next video and the next chapter. For now, we do need to talk about average velocity. Average velocity and average speed are not the same thing. They can be the same thing, but they might not be the same thing. I'm going to represent average velocity with a V, again for velocity, and a subscript of AVG for average, just to simplify it down. The average velocity of an object is defined as the change in position. So remember, S is one of the variables we can use to represent position. So a change in position divided by some change in time. And again, delta always means the final value minus the initial value. So we can write this as S final minus S initial divided by T final minus T initial. It turns out, since position requires an origin, so when we say position is how far, we mean it's how far from a specific origin. So position, say if my initial, going back to my example of driving from home to work, if my initial position is home and my final position is work, my delta S would be 15 miles south. Okay, because I'm taking my final position, my work position minus my home position. So I've traveled a total distance of the 15 miles I said before, and I had to drive south to get from home to work if I lived north of there. The delta S we call displacement, it tells us just simply where we ended up relative to where we started. If I want to talk average velocity, I would then, come down here, average velocity. Oh, that was wrong down here. This is average acceleration. Sorry. This equation is average acceleration. Average velocity would be 15 miles south divided by that 15 minutes, which was a quarter of an hour. So my average velocity would be the 60 miles per hour south. But I could ask a different question, and instead of talking about going to work, I could define my initial position, home, and I want to find my average velocity by the time I get home again. So not initial, but final position to be home. Now, the total distance I drove, assuming I just went straight to work and straight home, would be 30 miles. So 15 miles to work, 15 miles back home. The total distance I traveled would be 30 miles. If we're only accounting for the time that I was driving, the total time would have been 30 minutes. And so my average speed would still be the 30 miles. Now in half an hour, that still gives me the same 60 miles per hour. But my average velocity would be 0. That seems really weird because of course I had to drive to get to work, and of course I had to drive to get back home. But the average velocity would be 0 because the first leg of my trip would have had me traveling 60 miles per hour on average south, whereas heading home, I would have on average been traveling 60 miles per hour north. So these together, those directions cancel. The average velocity is 0 because of the delta S being 0. If I end up where I start, my final position is home, my initial position is home, there's no displacement overall. It doesn't matter how much time it took. No displacement overall leaves us with an average velocity of 0. Now, as we get into the next chapter, we're going to talk a lot more about instantaneous values, again, as I mentioned. And typically that's what we want to know more than just these average values. But I want to take a few minutes and talk about what we mean by acceleration and these directions when we talk about our vectors. So let's get a little extra space here. So in general, acceleration. Again, the physics definition of acceleration is that there is some change in velocity in a period of time. Because velocity is speed and direction, we can change speed. So acceleration means if we speed up, that is an acceleration was required. We could also slow down. That's a change in speed. But the physics definition of acceleration is any change in velocity. So we don't necessarily have to change the speed. Simply if we change the direction, then there is an acceleration. That one's typically new to us, for if physics is new to us. So the physics definition of acceleration involves speeding up or slowing down and or changing direction. I mean, technically we can turn a corner driving our car or riding our bike and speed up or slow down in the process as well. So it is possible for our acceleration to simply do both. Now, when we talk about acceleration and its units, I guess I should mention our SI units. In our course, we are going to be solving problems and giving our answer in SI units, the International System of Units. SI units are meters. So distances are in meters. We use just M. Time is in seconds. We'll use an S to represent that. Mass, which we will talk about later, will be in kilograms. These are our SI units. So position or displacement will have units of meters. Velocity and speed will have units of meters per second. So instead of miles per hour means miles divided by hour. We are going to use meters per second instead. So we will need to be able to convert our units, which we'll go over in another video if you need a refresher on that. Acceleration, our units, because it's a change in velocity over a change in time, acceleration has units of meters per second for the velocity, for the delta V, over seconds for the delta T. So we will see that in meters per second squared. What this means, for example, going back to gravity, saying that the acceleration of gravity is 9.8 meters per second squared, means the velocity of a ball, for example. If I tossed a ball in the air, the velocity of that ball will change by 9.8 meters per second every single second. So if I threw a ball upwards at, 15 meters per second, so I would call this time equals 0. After 1 second, so at time equals 1 second, the ball will still be moving upwards. It will have slowed down. Its velocity will be 15 minus the 9.8. So 5.2 meters per second. That's what we mean. For any acceleration at all, the numerical value is how much that velocity is changing by every single second. Now, in terms of the directions, when we talk about our velocity, our position, our acceleration, all of those being vectors, we need a way to describe the direction of those vectors in any given problem. To do that, we always do so using a coordinate system. So we always need to define some sort of x-axis, y-axis to work with. Since we're doing pretty much everything in 2 dimensions throughout the semester, I'm just going to use, for now, a traditional Cartesian coordinate system where x is horizontal, y is vertical. And I'm going to define it the same way we do when we work with our coordinate system. To the right means positive x, meaning to the right of the origin, means positive x. To the left of the origin means negative x. Up means positive y. Down means negative y. Now, when objects start moving through, like, imagine somebody hitting a golf ball. The golf ball obviously does not move in a straight line. It gets more involved to describe how things are changing both horizontally and vertically, which we're going to get to. But it's a little more involved. So right now, just as a reminder, we're going to talk specifically about linear motion, straight line motion. So whatever object we're talking about could be moving to the right, it could be moving to the left. Right and left, those would be a straight line. If that's the case, moving to the right will be positive because in our Cartesian coordinate system, to the right, that's a positive x value. To the left is negative. So our object, whatever it may be, is either going to be moving horizontally or vertically. We will talk about, like the child on a slide, moving at a slant or along a slope, but we need to talk about x and y first. So right now, let's just assume whatever object we're going to talk about is moving left or right. So let's say we have a car. And that car is driving from our perspective to the right. Let's just talk it conceptually. So a velocity to the right, let's say this is time equals 0. And we know by watching it that it's slowing down. So we could say after 1 second, it's still moving to the right, but it's not moving as fast. I'll call that a V1, this one a V0. And it continues slowing down. So this V2 at time equals 2 seconds is smaller. And then let's say it stops. V3 is 0. To represent the direction for position, velocity, acceleration, we are going to, like I said, talk about our coordinate system. So looking up at this Cartesian coordinate system, with this motion only being horizontal, all I want to think about is the x-axis. To the right being positive, to the left being negative. For position, we must define an origin. So if you were solving a problem in the homework, and they were asking you whether the position was positive or negative, they would need to draw where the origin was in the picture. Here, that's not drawn. So I will draw one in to talk about that. So for example, if the origin was down at time equals 0, where the car started, if the starting point, the origin was where the car started, and the car ends up all the way over here to the right, we would say the position is positive. Because now the car is to the right of the origin. As we go through and solve problems, it turns out we can choose our origin, or in a problem, it's quite possible that the author gives us a picture saying, hey, you know what, let's say the origin's right here. If that were the case, and they wanted to know whether the position was positive or negative, initially, I would draw a line from the origin back to where the car was initially. The initial position, because this arrow points to the left, because this car is to the left of the origin, I would say this position is negative, simply because it's to the left. So again, it's all totally tied back to the coordinate system we are using. If they wanted to know whether the final position, when the car's all the way over to the right, we would draw an arrow from the origin all the way to that final location of the car. Because that is to the right of the origin, we would say that's a positive position. So position, we always have to have an origin defined. If our homework is asking for just flat out, is position positive or negative, there has to be a picture or some sort of wording to explain where the origin is. Velocity. Velocity does not need an origin. The sign of velocity, so whether it's positive or negative, depends on the direction the object's headed in. So these original arrows I drew, I was explaining this car is moving to the right. It's still moving to the right, but slower. Still moving to the right or slower. In all three situations, we would say this is a positive velocity. At time equals 1 second, it is still a positive velocity. It's not as big, the numerical value is smaller, but it's still positive simply because the arrow points to the right. Same with time equals 2 seconds. It's a positive velocity because this car is still headed to the right. Now, when we say velocity 0, we don't need plus or minus because that doesn't have a meaning. It's not moving at that moment, so right or left doesn't have a meaning. So to figure out velocity, the sign of velocity, draw a sketch that includes an arrow pointing in the direction the object's headed in. Is it moving to the right? Is it moving to the left? And your arrow itself, if we come back to the original diagram, the direction of your arrow, since it points to the right, again, coming back up to this coordinate system, to the right means positive. So velocity, if I have, for example, let's say I have an object moving horizontally, and my origin is right here. I'm going to just write an O above that to represent origin. If I have a car and it is traveling to the right, and then a second later I see it slowing down, a second later it's slowing down, and then stopped. The velocity here initially is positive, even though the position here is negative. Okay? The position specifically depends upon where the origin is. The velocity specifically just depends upon which way the arrow is headed. So, for example, at this second point I drew, I would say this position is still negative because it's still to the left of the origin. But the velocity is still positive because that arrow representing the direction the car is moving in is still pointing to the right. The velocity here would still be positive. The position here now, though, would be positive because this car is to the right of the origin. At this final location I drew, the position is still positive because the car is to the right of the origin, but the velocity is 0 because it has now stopped. All right, let's talk acceleration for a minute. Now, acceleration, again, similar to velocity, let's change the acceleration. The sign depends on the direction of the arrow that you draw. Now, that's a little vague, and acceleration is typically the most confusing part of physics at this point, because we fundamentally want to think a positive acceleration means the object speeding up, a negative acceleration means the object slowing down. But that's actually not the case. It could mean that, but it might not. What I want you to do whenever you think about acceleration, think about, so instead of this diagram over here to the left being a car, imagine it's a kid in a wagon or a friend on a skateboard. So a friend on a skateboard, they're riding to the right and they're slowing down. What you want to think about is if the only reason they were slowing down was because of you, think about what you would have to do to change their velocity. So in the case of this example to the right, if you were the one to slow your friend down, you would have to push opposite. So when I say think about what you would do, I mean a push or pull. It turns out all accelerations are due to some sort of force. Technically, some sort of net force, which we're going to talk about in the second section. So not quite yet. That's why if acceleration is a result of having some sort of net force, that's why you can think about what you would have to do to change the velocity. If I would have to push on my friend to the left in order to make my friend slow down on their skateboard, that means the acceleration would be to the left. Now, granted, a car driving down the street is not somebody pushing on it, but there is a force opposite the velocity that's making it slow down. In this case, in this specific coordinate system, because that acceleration vector points to the left, that acceleration is negative. And again, that just has to do with this whole x-axis, to the right positive, to the left being negative. Let's throw a different scenario out there. Let's say, let me throw in a coordinate system. Let's say we have some sort of object. It's traveling to the left and it is speeding up. So it's going faster and faster and faster. So all these arrows represent our velocity. Because those velocity arrows point to the left, that means the velocity is negative at all of these moments in time. So this first point would be time equals 0. This one would be time equals 1 second, just to get a representation. Of the motion. Now position, at this moment in time, the position is positive, simply because the origin is over here to the left, this object is to the right, that means the position is positive. And that's true for these first three cases. Over here to the left, this position is negative simply because the object is now to the left of the origin. So velocity is negative in every situation simply because the object is heading to the left the whole time. Position goes from positive to negative because of crossing the origin. Now let's talk acceleration. Acceleration. If I have my friend on a skateboard, they're moving slow, and I want to make them continue in the same direction but move faster, I want to make them speed up, I would push on them in the direction of travel to help them speed up. Because acceleration is a result of the net forces, we can say that the acceleration in this case has to point to the left. That is how we're going to speed up. But over here, remember this previous situation, we said the push was negative. Well, that's true again. This push is negative because it's pointing to the left. In this first case, this object slowed down. The negative acceleration means slowing down in that situation. But in this second situation, this one is speeding up. It's going faster and faster. Yet the acceleration is still negative. Positive and negative, whenever we're talking about directions of any of our vectors, positive versus negative, is always due to our coordinate system. So that's why in this second case, even though the acceleration's negative, the object's speeding up. So really, we do have a general rule that we can say. We can say that if velocity and acceleration point in the same direction, so like this second case, acceleration and velocity are both negative. If velocity and acceleration point in the same direction, the object is going to speed up. That means they both point to the left or they both point to the right. Okay? If the velocity and acceleration point in opposite directions, the object will slow down. That's always true. Now, in terms of turning, if I'm like driving down the street and turn the corner, that actually is no longer linear motion. So it's not quite as simple. But if I imagine looking down at my car and I'm driving, yet I'm going to turn, I have to have an acceleration that points towards the right, that allows my car to turn. And that ends up being due to the friction between your tires and the road. But we're going to talk about that later, because right now, when physics is new to us, which I'm assuming is the case, it's enough to practice with speeding up and slowing down. You will find that a rough sketch, it does not need to be pretty. A rough sketch is necessary and, well, extremely helpful, I should say. I will always use a rough sketch just to get an idea, especially drawing the velocity vectors, the acceleration vectors, drawing in my origin. It helps me choose those signs. And those signs are absolutely essential when plugging the values into the equations. Now the rest, ultimately the finalization of these introduction to concepts of motion is what is called a motion diagram. Which you've actually just seen. If I draw some dots, say I'm not going to draw the velocity at the moment, but if I say at time equals 0, I have an object at this location. And then at time equals 1 second, I have an object here. Time equals 2 seconds, I have an object here. Time equals 3 seconds, I have an object here. I'll stop at 4 seconds. We should be able to look at this situation versus start with an object at t equals 0. And then have our object at t equals 1 second. But then t equals 2 seconds is over here. T equals 3 seconds is over here. T equals 4 seconds is at the other end of the screen. We should be able to distinguish and explain or describe the type of motion that we're seeing. In the first situation, we can see the objects moving to the right, simply from the time markers. If time equals 0 is the left dot, and then 1 second is the next one, 2 seconds, 3 seconds, so forth, this object needs to be moving to the right, which means a positive velocity, of course. Now, another thing we should be able to notice and observe is whether or not there is an acceleration. Again, acceleration means the velocity needs to be changing. If I look at the spacing between these dots, that distance is the same. If the distance between dots is the same, we are implying that this object is covering the same distance every second. That means a constant velocity. The same speed, the same direction, every single second. So I could come back and draw the velocity the same length every single second. But if the velocity is constant, meaning it is not changing, that leads us to acceleration of 0. 0 acceleration means no change in velocity. Okay. Looking at the second situation, time equals 0, we will have a velocity. Time equals 1 second, though, I need to draw it a little longer, simply because I'm seeing a bigger distance, and then another bigger, even bigger distance, and even bigger. So as this object travels for 1 second, it's covering more and more distance, and I don't have enough room to draw that last one. We see this object speeding up. Well, acceleration. There's an acceleration if the velocity is changing. So if there's an acceleration and the object's speeding up, that acceleration has to be in the same direction as the velocity. So these velocities are positive. This acceleration would also be positive to speed up. In terms of starting physics, brand new, this positive and negative sign tends to be one of the most challenging parts. So again, as we look for solving any problems, if there is not a coordinate system already drawn in the problem, draw one. Draw the arrows to represent velocity and acceleration, because saying they're positive or negative is based off of the coordinate system. I'm not going to walk through up or down, but it's because it's essentially the same thing. We would just say up is positive and down is negative. That's still linear motion, so it boils down to the same thing. As we continue moving and talking about motion, we will be doing some examples and finding the equations that solve for instantaneous position or velocity or acceleration. So where the object is at a specific moment in time. What's its velocity at a specific moment in time? What's the acceleration at a specific moment in time? And that's, to do that, we move into the next chapter. So we'll continue with that in another video.